In today's video, we're looking at radioactive decay, an illustration using dice, sometimes called radioactive dice, but they're not really radioactive. They just have one side coloured a different colour. I spray painted these. I pushed them all close together and sprayed them, but you can now buy dice ready painted one side. We have sets of about 120, and the idea is that we throw all the dice into a tray and then pick out the ones that have landed coloured side up. I'm actually arranging these in the corner of the tray because I'm going to get a graph plotted using the dice like a bar graph. We would normally get the students to count the ones that have landed coloured side up and then remove them from the next throw. So the remaining dice have not landed coloured side up. We're going to throw again. And again, the ones that have landed coloured side up, we move to where we're plotting our graph, or count them and record them if we're doing it in class. And you need square-sided trays if you're doing this graph plotting, bar graph plotting type thing, which normal grapnel trays aren't quite suitable for. We have these cheaper version that I keep specifically for this class demonstration. The sample size of 120 means we can do it in a sensible amount of time doing a lesson, and can lead to discussion about the numbers, the fact that if we had a larger sample size you would get a better curve, and sometimes we can do that by adding all the class results together and plotting them. So again, I've collected up the ones that didn't land coloured side up and thrown them again, picking out the ones that did land coloured side up from that go, and arranging them into a bar graph. There was only one of those two that landed coloured side up. Collect them up again for a fourth throw. So you're getting fewer dice, fewer nucleuses to decay each time. Same percentage of those are decaying, but because there's less to start with, fewer to start with, the numbers that we're getting landed coloured side up will reduce. Now in theory, you never really get down to 0, but with such a small sample in sort of a radioactive substance, because of the huge number of starting nuclei. But with the small sample size of the dice, of course, we will get down to 0 eventually. So only 4 decaying in this one. There was only 4 decayed in the last one actually as well. Only 1 in that one. But 5 in that one. So it's quite random. We don't get as good a graph with small numbers of dice, but this normally gives us relatively good results. Do a couple more. Only 1 again in that one. 2. Let's just do 2 or 3 more. 4 again. Only 1. 2 in that one. We're only down to 4 left. Down to 2 left. So none, so we're going to leave a space. None, so we're going to leave another space. None, so we leave 3 spaces. None, so we're going to leave 4 spaces. None, 5 spaces. 6 spaces. 7 spaces. 8 spaces. 1 there. None. And we could go on quite a long while perhaps with that. Okay, let's have a look at our bar graph of this decay. So that's modelling radioactive decay using dice that are coloured one side. Now I should have mentioned with that using dice to show radioactive decay that we're looking for half-life. So with 120 dice, with 1 out of 6 sides coloured, there should have been, according to probability, about 20 of them landed coloured side up in the first throw. So that leaves about 100. And in the second throw, 1/6 of 100 will land coloured side up, according to probability. So that's fewer. And we're looking at the number of throws until half of those original dice are left, or half of them have decayed, and the activity, the number of dice that are landing coloured side up, will be down to 10 each throw as well.